Well, hi guys. Hi everybody. I guess guys, girls. I'm gonna do a tutorial right now on a 2D heat transfer with Ansys 12.0. This is basically the geometry. It's pretty simple geometry. There's nothing complicated about this problem, but the point is that this problem is useful because with the steps that I'm going to show you right now, you should be able to do most of your 2D simulations dealing with heat transfer, and you can make the geometry more difficult if you want. You can change the numbers here and there, but overall it's going to be pretty much all the same steps. So let's get right into it. You've got this geometry. It's basically a plate with a hole in the middle. Top surface is insulated. You've got a constant temperature on the right, constant temperature on the left, and then you've got a heat flux coming in from the bottom, convection in the center, and you've got a thermal conduction coefficient K. Let me just scroll down to the problem description. Okay, so thermal conductivity of 25 watts per meter degrees Celsius, and also has a heat generation rate of 30 watts per meter cubed. So let's get to it. Let's start. So open up your product launcher. What you want to do is create a file ahead of time. So if this computer wakes up, we might get something done today. So create a new directory, heat transfer example, that's what I'm going to call it. Okay, and now go ahead and browse, find that folder. Sorry, this computer is just, I say it all the time, and maybe you guys are starting to notice it, that basically I'm working on a ghost drive and it can be really slow sometimes. Then it picks up. So hit run, that'll open up Ansys. Alright, I like to work on a white background. Go to style. There's just some things I do. You don't have to do, but I like to do them all the time. Reverse video. I also am in the habit of putting on a title. Heat transfer tutorial. Click OK. Okay, and if it doesn't show up right away, go ahead and replot. Now it showed up down here. Hit your preferences. We're going to do thermal analysis. Click OK. Preprocessor. Going to choose the element type. Add. And we're going to do plane 77. So let's find that. 8 node 77. Okay. Close that. And go ahead and save if you'd like. There are no real constants for plane 77, but if you wanted to double check that, it doesn't hurt. You can try to add a constant and it won't let you. Just like that. Okay. So go into material models, conductive, isotropic, and if you recall, we said that our thermal conductivity K coefficient is 25 watts per meter degrees Celsius. So we went ahead and we put that in, save. Now we're gonna start with some pretty useful tools in terms of areas if you're not used to doing it. We're gonna make the outer rectangle first by 2 corners. I'm gonna put my first point at the origin, and then the width and height, let me just check the geometry. You have to always make sure that you're using the right units. So I'm going to input my units in meters, and these are all in centimeters. So it's going to be 0.08 plus 0.1 plus 0.1, that's 0.16 plus 0.1, that's 0.26 is the width, and then the height is 0.3. So let's get back to this. The width said 0.26, and then the height, where'd my mouse go? There it is, 0.3. Okay, press alright. Now we've got a square, and okay, so we just made the square. Now we're going to make the inner circle, and let's just take a look at the dimensions. So we've got the diameter of this circle is 10 centimeters, and the center of the circle is at this is 26, so it's right in the middle, it's 13, and then the height is 30, half of that is 15, so it's 13 by 15. The diameter is 10 centimeters. Oops, wrong one. So we're going to create areas by circle, solid circle, and then the x is going to be 0.13. The y is going to be 0.15. And the radius, the diameter was 0.1, so the radius is 0.05. And the moment of truth, let's see if that's right. Okay, that looks right, good. So here we can go ahead and save if you'd like. Now this is a pretty useful tool I'm about to show you when you're modeling inside of here. You can also model outside of Ansys, but if you want to model inside of here, it's good to know that how to delete or subtract two areas from each other. So go to Operate, Boolean, and Subtract. Areas. You can also do volume. Now it's kind of tricky, but you have to choose the larger area. Okay. And press enter, and then choose the inner area, press enter, and it has been done. Let's just go ahead and plot areas, make sure if that was done correctly, and let's do numbering controls. Let's number the areas, make sure that we're doing well so far. Okay, so that's correct. We only have one area, and it's called Area 3. Area 1 was our square, Area 2 is our circle, now Area 3 is this plate here with the hole in the middle. So that's a good tool to know about. Now our modeling is finished. Let's save, and I can move on to meshing. Meshing, you can do this many different ways. I didn't want to press that button. I want to do this. You can set the global attributes there. If you have different ones, you can change that. And I'm going to set the lines. Actually, I'm going to pick all and do 10 divisions per line. And where's my mouse? There it is. Press OK. And let's go ahead and mesh areas. And you know, it's not too bad. I wonder, I'm gonna try this. I'm gonna refine this elements. Pick all. Okay, so you can refine it as easily as that. So it's pretty, it's an okay mesh. We're gonna accept that mesh and move forward. Let's go ahead and move to loads. Define loads, apply, and thermal. And let's first set the two constant 100 degrees on both of these lines. So temp 100 and press OK. Alright, so going back to the code, we got 100 degrees Celsius on these two walls here. Now the next thing we can do is we can apply the convection in the inner surface. Our H is 55 and the temperature is going to be 5 degrees C. So let's see, we're going to apply thermal convection on lines. Go ahead and choose the inner lines. That's 1, 2, 3, and 4. This circle was divided into 4 lines. Click OK. Now the film coefficient is at 55. That's our H. And then the bulk temperature was 5 degrees Celsius. Click OK. And then the last thing, actually not the last thing, but one of the second to last thing we need to do is apply the heat flux. Let me just remind myself, 500 watts per meter squared heat flux, and we're going to apply it to the lower area. Select that area, lower line, click OK, and the heat flux value is 500. OK, press OK, and then the last bit is heat generation on areas, and this is the area, but before, let me just remind myself of what the actual value for the heat generation is. 30 watts per meter cubed. 30 watts per meter cubed. Now, I just actually am thinking right now, the units that he gave, that this problem is stated, it says 30 watts per meter cubed, and I'm starting to think that I need to convert that number. Let me see, let's list areas. The area of area 3 is stated here. 0.07015. So, you know, if I'm wrong about this, please don't, you know, crucify me. But I'm going to convert that number because we're working in meters squared, and the number given to me was in meters cubed, and I believe that that's the correct thing to do. So let me just get a calculator out really quickly. And what do we have? We have meters squared, so it's got to be multiplied. So it's 30 times 0.07015, 2.1045. Okay. So we're going to do heat generation on areas. Okay. 2.0145, and press OK. And so now we've added all of our constraints or loadings, right? And the next thing we're going to do is solve. Current ls, press OK. solution is done. Perfect. Click OK. Click close. Close this. And there's a ton of things you can look up in post-processing, but let's just do some of the basics right here. Contour, nodal solution, and the most satisfying is usually the nodal temperatures. So look at that. What have we got here? Remember, we're working in Celsius, so this is heating up pretty hot on the edges. Well, we would expect that, right? Because the edges we set to be 100 degrees Celsius. Now in the center, where the convection is happening, and remember that, I guess you could imagine this as a pipe going through the center. That's at 5 degrees Celsius, and that's at 87 degrees Celsius right along this wall here. Let me see. You can also do other things like the flux. And you can also, let me see. I don't really want to get into path operations. Well, alright guys, I hope this helps somebody. Again, you can, play around with the post-processing, the outputs and everything, but at least now you know how to work a 2D problem on Ansys, and you know how to do quite a bit because of the tools that I've just showed you. So thanks for watching, and I hope it helps somebody. So long.